And I have the pleasure of presenting our third award candidate, Ms. Ziyan Go from University of Hong Kong, and she's presenting compact design of a hydraulic driving robot for intraoperative MRI-guided bilateral stereoscopic neurosurgery.
Good morning. I'm Ziyan, a PhD student from the University of Hong Kong. Today, I'm very happy to stand here to present our progress of a compact robot for MRI-guided stereotactic neurosurgery. Stereotactic neurosurgery involves a technique that can locate the target inside the deep brain region. It has been widely adopted for different applications such as needle biopsy, drug delivery, tumor ablation, and deep brain stimulation. Let's use DBS as an example, which is a treatment for Parkinson's disease and epilepsy. Electrodes are implanted to those tiny targets. For example, the nucleus in the deep brain region, the surgery is tremendously demanding on accuracy on the scale of millimeters, so as not to damage the surrounding critical structures in brain. The surgery manipulation seems to be very simple, just inserting a straight needle into the brain. However, once an entry burr hole is made, the cerebrospinal fluid can leak through the burr hole, resulting in brain shift. This alone can degrade the needle insertion accuracy, risking the insertion far beyond the target. Unfortunately, during the surgery in the current practice, we can neither see the needle tip nor the brain target shift. Without intra-op MRI, this procedure can be very time-consuming. It will take at least 6 hours to complete it. The reason is that the patient has to be awake under local anesthesia. The surgeon expects the patient to give verbal feedback quite often and even perform an intensive motor task to ensure the needle insertion is going well. Microelectrode recording is also needed in every small step of insertion. Basically, for this stereotactic, we want to see both the needle and the deep brain target. There's no doubt that MRI is the only imaging modality and can do it. Unlike CT or X-ray, it doesn't generate any harmful radiation during the scans. MRI can also visualize any physiological changes of the soft tissue. For example, the tumor ablation temperature can be monitored under the real-time MR thermometry. The current advances can also offer very fast imaging sampling, even for catheter navigation inside the heart chamber. Despite these MRI advances, the question here is why we need a robot to assist the intervention guided by MRI. Let's put an example here. With MRI guidance, the patient can be under general anesthesia. This commercial system is called ClearPoint, and it's not a robotic system. The aiming platform must be manually adjusted using many long and flexible screwdrivers. It looks like fishing, but fishing with many rods. Too many surgeons fish and drive the two separate mechanisms on the left and right, just to point the needles to the target. However, the fishers will not have instant feedback about the pointing accuracy until working in and out to see the intra-operative MRI on the computers. Therefore, teleoperative robots can be very useful to improve the surgical workflow, but making a robot capable of operating under the strong magnetic field is indeed very, very challenging. No ferromagnetic materials is allowed in the MRI room. For instance, the EM motors, currently there are very few prototypes for this surgery. There are 4 notable robots: NeuroArm from Calgary, NeuroBlade from Monterey, the RCM robot from WPI, and Robotics from Georgia Tech. All these robots are driven by piezoelectric motors to reduce the EM interference EM shielding of the motor must be very sophisticated, but it may still inevitably degrade the image modality due to the electric signal of the cables. Size is another concern, not to mention the bilateral needle insertion. Existing robots are too large to be incorporated with the standard imaging head coil, with some that cannot be fully operated inside the MRI board. Therefore, our first contribution is to develop a totally MR-safe teleoperation system that doesn't generate any EM interference. No image artifact can be found with and without robot actuation. Here, we propose a clean transmission system with hydraulic sealing component named rolling diaphragm. Unlike conventional seals using O-rings, this diaphragm can flip inside out to roll along the inner surface of the cylinder. This enables very low friction of transmission, hydraulic transmission. In this video, you can see the master actuator is driven by the EM motor in the control room. Hydraulic transmission is about 10-meter pipes through the waveguide, which is the only channel connecting the two rooms. The slave actuator in the MRI room can synchronize the motion very well. This diagram contains a series of experimental results showing a good picture of how this transmission hysteresis is very small at different hydraulic preloading pressures. Up to the point, the pressure can be increased to further enhance the transmission stiffness and also minimize the mechanical backlash. The second contribution here is the robot structure. The compact robot design requires only one single incision in anchorage that can accommodate two independent manipulators. In total, there are 4 degrees of freedom for each manipulator, which can also be easily mounted with the anchorage. Each joint is coupled with a pair of tendons driven by the hydraulic actuator. In general, the overall objective is to maintain the accuracy. Once the insertion trajectory is confirmed with the MRI images, it can offer a firm and rigid platform for the needle insertion. A linear actuator driven by the hydraulic transmission can also be integrated with the needle guide and the manipulator. This actuator can advance the needle with very fine resolution. The third contribution is to develop a robot tracking system, closing the robot control loop. The existing MR-guided robots only incorporate with passive markers. These are only reviewed on the imaging domain at very low sampling rate. I can say that the active markers may be the only solution to achieve fast and automatic robot checking inside the MRI. However, the conventional active marker requires connections to the scanner wire cables. Again, this is not practical to deal with electric cables if we have many markers. That's why we have developed our own wireless version, which is wireless circuit capsulized in the needle guide. This multi-layer circuit is fabricated on a flexible PCB as thin as a paper. To our knowledge, this is the smallest ever reported. Our marker can wirelessly resonate with the MR lambda frequency of the scanner, given our very high intensity signal contrast. The configuration of the needle guide can be augmented on the images based on those marker coordinates, acting as a collimator adjusted in real time. If we apply MR image sequences, we can reveal bright spots on the images. The intensity could be far higher than even water or gadolinium material. Here is a video showing a caster integrated with 2 of our active coil markers, which is being checked inside a phantom heart atrium. The checking can be measured in imaging domain directly without having to do any registration. Instead of imaging, we could apply the pulse checking sequence to pick up the high contrast signal automatically at the frequency of 40 Hz without any imaging reconstruction. For this robot, the performance metric seems to be very simple. It's mostly about the targeting accuracy. Mechanically, our robot could achieve less than 1.8 millimeter error, already outperforming DBS without a robot. However, to successfully translate our robot into the clinical practice, the significant improvement over the current workflow is in fact our major concern. We like to present our ongoing cadaveric trial, which is how we validate the ultimate benefits in terms of the workflow efficiency. The robot mounting, this is the setup in the MR room. The robot mounting on the head doesn't require any extra mounting on the MR table. The installation is very straightforward. An MR conditional camera was set up to observe the teleoperation just for safety. All those real-time imaging and checking data will be streamed into our navigation interface in the control room. Here's the schematic showing the workflow, either with or without the robot. Pre-op MRI scans are also conducted for surgical planning, and the burr hole and accurate incisions will have to be prepared in the operating field. However, with robot assistance under MRI, our validation demonstrates the tedious and repeated process can be eliminated. Here you can see that the subject head was fixed with our robot within the size of a hair coil. The tool manipulator will then be teleoperated inside the bore, orienting the needle guide to the deep brain target. Once the needle insertion trajectory was confirmed, the subject head was moved out for the operator to advance the needle half of the way, then driving further to the target in final resolution. Finally, here, I would like to summarize our work novelties in 3 aspects. Well differentiated from the state of the art. This is the first robot capable of performing bilateral needle manipulation based on only one single invasive anchorage. The compact robot design can be accommodated inside a standard head coil for imaging and intervention. The robot hydraulic actuation is completely MR safe and provide high fidelity transmission over the long range. No EM interference will be induced on the images. Using our miniaturized wireless checking coil, the robot and the needle can be localized directly in the MR coordinates in real time. We don't need any calibration or co-registration between the imaging and tracking domain. It substantially reduces any error due to the manual selection of the fiducial markers in the images. We believe all these components can be applied to other MRI-guided interventions, for example, cardiac catheterization or prostate breast biopsy. That's all for my presentation. Thanks again to our collaborators. I hope to explain further our robot mechanism in my poster at Pod C8 this afternoon later on. Please come over to chat with us. Thank you.
We have time for a couple of questions. Questions, so I guess I will ask one. So with regards to the fiducial that you presented, how does this fiducial compare to some of the conic section fiducials or helical fiducials for MRI pose detection that were developed in the past? Why did you choose this specific fiducial geometry, for example?
Actually, we developed a MR-based checking coils for the give the positional feedback of our robotic instrument. Actually, the main features of it is it can be very provide very high update rates. The positional checking in the imaging domain directly from we can apply the checking pulse sequence to obtain those positional feedback, and without the imaging reconstruction, because the imaging reconstruction may take maybe very time consuming, and if we use the passive fiducial markers, we cannot do the real-time checking at very high rate. Yeah.
Any other questions from the audience? Okay. All right. One last question. Your system combines wire actuation with hydraulic actuation. Could you elaborate why combining both of those as opposed to just simply using wire actuation?
Actually, because the transmission distance is very long. It is over 10 meters, and we have the robot will be set up in the MRI room, and the surgeons will control the robot in the control room. And there's only one waveguide. We can pass the hydraulic tubes through this waveguide. The waveguide diameter is very small. We cannot pass too much transmission components through it. And considering the compact design that we use the tendon-driven for the manipulator joint actuation, and because the hydraulic actuator is relatively large, so we put it on the surgical table and connect with the joints via the tendons. Yeah.
All right, let's thank our speakers again. Thank you.
So this brings an end to the session. I think the next session chairs, are they here? Okay.